Hi, good afternoon and salam sejahtera, ladies and gentlemen. Thank you for taking your time off to attend this presentation. My name is Ping Hing and I'm from Swissma Building Technologies. And today I'm happy to have here a guest speaker, Mr. Rocky Shet, the Technical
Hi,
Marketing Engineer. Hi, Rocky, from NS
hi.
BlueScope Malaysia. So Rocky will help to take care of the first part of the presentation, explaining what is BS8414. So after that, I will come in on the part two to share the experience we had doing the 8414 test and also on other subject matters. So are you all set and ready, Rocky?
Yes, definitely. Thanks,
So
Mr. Lau.
then over to you now.
All right. Thanks, Mr. Lau. So prior to introducing BS8414 and the requirements needed to pass the test, let me just give you a bit of context, the importance of it, and also prior to this test, what was the measure done, in Malaysia, right, to curb those cladding that could potentially catch fire. So of course, this is a hot topic. Amid the incident happened back in 2000, I think 17, of Grenfell Tower, right? So the picture that you can see here is really sad story where I think 72 fatalities after this incident, and it was actually caused by a simple fire, right? So the context of this story is this: in the early like midnight, around 1 a.m., there was a fire, that broke out from this building. I mean, this unit at fourth floor, right? And the fire actually broke out of the window and then started so-called spreading outward. And it took only 20 minutes for the fire to spread from fourth floor all the way up to 24th floor, right? Within 20 minutes. And it didn't just spread upward, but it spread around the building. So as you can see here, it actually completed one circle by the time it reached morning. And the fire was not extinguished, by the time, it reached early morning. And what you can also see is that fire actually broke into those different units and then caused fire, right, spreading inward. And of course, upon investigation, it was found that the cladding that was used to retrofit the building is called conventionally aluminum composite material, right? And there's an infill that is polymer, polyethylene. Okay, and this infill itself is the one that is the major cause of the fire spreading. All right. So of course, this is not unique to this Grenfell issue or Grenfell incident. It is also seen in various occasions throughout the world. And in Malaysia, prior to the Grenfell Tower incident, I found one back in 2016, where the fire actually spread it, due to ongoing maintenance work that was done, right? So the maintenance work involves some heat, some fire perhaps, and all of a sudden the cladding caught fire. And what you can see here is that the fire quickly spread across as well. So it's very similar to the Grenfell issue, and it was identified that there was certain type of polystyrene used in the cladding, and the cladding itself create, of course, hazards. But luckily for this incident, there was no fatality. And of course, the more recent one was the KWSP-PJ incident, where again there was a maintenance work going on the external, building, and the fire caught on and spread, across very very quickly. And this is very similar to the example shown earlier. And upon investigation, it was found that the cladding itself did not meet a certain requirements or safety requirements. And that particular reason seems to also be that there is certain polymer, or they call it polyfoam, used in the cladding. Okay, so the question is, with the existing or so-called previously existing system or regulation, why did this incident still happen, especially in Malaysia? So let me just put you in context. Prior to this BS 8414 test being introduced to test out the external cladding, whether it is suitable to be used and does not pose any fire incident or safety risk, is they use this thing called Class O, right? As what you can see from this red box. So Class O is less understood by a lot of people, and so the requirements for a material to be considered Class O is that it needs to be tested in this British standard BS 476 Part 6 and Part 7. All right. So later on, I'll briefly run you through it. And one of the other misconception is that people will always perceive Class O as non-combustible material, right? So a material that is classified as Class O need not be non-combustible. And also, I will give you a brief run through of what is non-combustible material. Right. Of course, the new one is actually BS 8414, which I will explain briefly how the setup works and also the requirements needed to pass, especially in Malaysia, because let's be specific, right? The regulation is enforced in Malaysia, right? So essentially, it is a fire test for building materials. All of these are. And the one that is more general is BS 476 Part 6 and Part 7. So these two tests itself combined together test for flame spread, right? So it tests whether the building material itself will spread fire. Okay, it's different from non-combustible, yeah. So part 6 goes like this. So this is a diagram of the jig, used to test the fire. I mean the interaction of the building material with the fire, and it tests for whether fire would grow exponentially or upward from the surface. And over here, the specimen, also called the building material, will be placed within this jig, and then there'll be fire source coming up front, from the surface. And of course, there will be various data that are more abstract being collected during this test. And once it is collected, then it will be calculated based on the standards. And of course, this test standard and also the calculation are more abstract, so I would not go into details about how it is calculated or what is the meaning of this. But essentially, you get two major results. One is fire propagation index, or I, right? And another one is indices I1, I2, and I3. Okay, so these will be used to check whether a material is classified as Class O or not. All right. So second test is BS 476 Part 7, where this one tests for spread of flame laterally, right, on the surface. So this is how the actual test works, or the setup works, looks like. And I actually got an external source of to demonstrate how it actually looks like during the tests. So this is how it looks like. So the sample will be installed perpendicular to the radiant heat, as what you can see from the big surface, and then there'll be an ignition point at the beginning, and they will test the whole thing until the fire subsides, right, or burn until all the way to the end. And as what you can see from this video, it seems like the fire actually started spreading laterally. Okay, so in essence, this Part 7 test, it will classify the material to be whether Class 1, as what you can see denote over here, Class 1, Class 2, Class 3, or Class 4. Where if let's say by visual, if let's say fire that was ignited over here by the flame torch and also the radiant heat, if let's say fire do not spread beyond the number 1, okay, then it'll be straightforward. It'll be classified as Class 1. And same thing, if let's say it does not spread beyond 2, but then it's within this, right, then it'll be classified as Class 2. Okay, so based on our observation, Okay, if let's say because they will actually test not just one sample, they will test 6 sets of samples. And if let's say the result shows that the fire do not spread beyond so-called the number 1 circle box, then it will be classified as class 1. Okay, so the combination of part 6, which is fire propagation index of less than 12 and sub-index I1 of less than 6, and also part 7, where the material is classified as class 1, meaning it do not spread across or beyond the box 1, right? Then combination of these two, then the building material will be classified as class 0. Okay, so there is no class 0 defined within these two standards. It is actually defined by building regulators. So in Malaysia, it is defined by BOMBA what is class 0, and you will see in building code and all that, they also refer back to these two test standards. All right. So the standard itself do not dictate what is the requirement, rather the test method. Right, except for part 7 where it classifies class 1, class 2, and so on. Okay, so in general, pre-painted product that has a very thin layer of paint layer would generally be classified as class O. Okay, so we have done our test. Our product are considered as class O. Okay, of course, having said that, this class O or these two tests itself has its own scope, right, or limitation in terms of its reaction towards the fire, bigger fire. Because if you have a material where the infill itself is combustible, or rather does not comply to these standards, or can catch fire, or even worse, those like polyethylene and so on that really adds fuel to the fire, these tests, part 6 and part 7, would not find out or determine whether those will happen or not, because they only test on the reaction of the building material surface. Right? If you have a composite panel, then they are only testing the surface. They are not testing the inside, right? And this is where it differs from BS A414, which I'll get into shortly. So of course, like I mentioned earlier, class O do not represent non-combustible, right? So non-combustible goes through BS 476 part 4 test. So non-combustible is actually a much more stringent requirement, because if it do not combust, then it will not spread flame. Okay, but if let's say it is classified as class O, it will not. It might combust, right? The paint film might get burnt off very fast, but it might not spread flame, meaning it might not cause the fire to spread, laterally or vertically, right? So that is what we mean by class O and non-combustible. Okay. So if you want to find out whether building material, homogeneous material, is considered as non-combustible, you have to go through this test, BS 476 part 4. Right. So over here, they will actually test 3 specimens or 3 samples of your building material, and of course come back with various requirements, which I will not drill down into. And in the end, it will actually give you an answer whether it's combustible or non-combustible. All right. So over here, we have done our test as well for those unpainted corrosion seal product, right? Example like zinculum, right? Those will be classified as non-combustible material, right? Without the paint film, right? And of course, it's safer because and because it does not catch on fire, right? Of course, moving on to BS A414, what does it mean, right? And how does it differ from those tests that I just mentioned? So BS A414 is actually a test for a complete external cladding system, right? So this is how it looks like, during the tests. And as you can see, I'm not sure whether you can see on the right side, there are actually 3 floors, right? Actually, the scale is bigger, much, much bigger, and the fire is much more severe than the earlier tests, right? And this test itself tests for a complete build up, right? For example, there'll be a testing of the fire breaking out from this chamber, and then see how the cladding interacts with the fire. And of course, a lot of things are taken into factors, such as the cavity space in between the, say, for example, masonry wall and the external facade or external cladding, right? Those are taken into account, absolutely. Okay, so the whole thing is to simulate how the cladding reacts to the fire, right? In plain and simple, description, right? So the intention here is that if, let's say, the whole cladding systems is installed, they want to see whether the fire that was started out from inside the building, for example, like the Grenfell Tower, where fire started out from the kitchen, as well as fire from the external source, for example, the KWSP or the Perpustakaan KL case. They will determine whether those two sources of fire would cause the external cladding to spread fire upward and around, right? So of course, ideally, you do not want that to happen. Otherwise, it will cause harms not to that one localized place, but spread all over the building. So of course, prior to installation, of course, this is how it looks like of the cladding. And then these are the test rigs. So of course, for BS 414, there are actually two parts, right? Part 1 and part 2, where part 1 actually is external cladding locking onto masonry wall, right? If you have a plaster wall and then you want to beautify it, adding a facade or external cladding, then go for part 1 test. If, let's say, it's actually a steel structure wall, steel structure where the cladding is locking onto this structural wall, then you go for part 2 test. In essence, there are only one difference where I'll go into later on, right? But the setup is more or less very similar. Okay. Okay, so this is the diagram of how each looks like in terms of setup. So there will be a main face and there will be a wing face, where at the bottom you can see this combustion chamber where the fires will be started, and then there will be fire source, which is actually a specific type of wood that gives us an approximate amount of heat, right? And of course, the cladding itself needs to be at least 6 meters high, right, above the chamber, right? And various other dimensions like the width and also the wing face, width. And there are actually a bunch of quite a lot of sensors to be installed as well. So there are 8 thermocouples. Actually more than that, because there are external and internal. But for level 1, which is 2.5 meters above the combustion chamber, there will be thermocouple, meaning temperature reading sensors. And then there is a more crucial one at level 2, which is 5 meters above the combustion chamber, right? So these two will be taken for consideration and also for evaluation whether it pass or fail. And the setup, for example, if, let's say it is locked onto masonry wall, then they will actually classify the most outer surface behind it or in between masonry wall and the most outer surface cladding. Those are classified as internal area, and the outer surface, right, it will be classified as external, right? Because why this is important, because they will actually place thermocouple at those places, and within that internal area, if, let's say, there are insulations that are thicker than certain dimensions, then they will actually insert thermocouple at the middle of that thickness, right, of that insulation, right? So there are a lot of sensors, I would say, right, that is needed to actually take readings of how this cladding interacts to such severe fire break out from the window. Okay, so this is how the sensors looks like, the external thermocouple. So it looks very simple. It's just a wire, but of course there are actually a lot of things that is connected to capture the reading. So just now I mentioned there are a lot of factors that needs to be taken into account. So these are some of the examples, which later on Mr. Lau will elaborate in more detailed manner because of the complete report, right? So things like the cavity space, or so-called the gap in between the masonry wall and the cladding, right? So those will be taken into account. So these are some of the examples. Or maybe the thickness of the cladding. So those are also part of the consideration when they capture it in the report, right? And the amounts of screws, the type of screws, the C channels, the thickness of all of that needs to be taken into account, because the requirements, also called the regulations, requires that the specific type of setup, with specific type of cavity space, needs to be tested to this BS 8414 and needs to be acknowledged by BOMBA, and they'll give you an approval for that specific spec. So after that, you can use the same setup for different kind of location that requires this test, right? Or different kind of project for that requires this test, right? So when it comes to requirement, it is similar to BS 476, class O, right? So it will not be stated in BS 8414. If you have the document, you read through the whole document, you will not find one section that will tell you how do I pass this test. No, right? Because each country, they'll set their own criteria, and of course Malaysia, since we actually adopted this standard testing standard from UK, British standard, we also adopt the requirements from their regulators, right? Building regulator or fire safety regulators, right? And this document itself or requirement is actually co-developed between CIRIM and BOMBA. So we do have the soft copy link after getting approval from CIRIM posted on our website. So it is a public interest document, so you can actually go and download it. Okay, so there are in total 6 requirements or 6 performance criteria, they call it, which you can call it, if let's say you pass all 6, then you pass BS 8414 test, right? So of course, out of the 6, the last one, system burn through, is only applicable for part 2, which is external cladding locked onto steel structure. Okay, so another thing that is exception is that this BS 8414 test is in Malaysia is only required for building above 18 meters height, right? Anything below that, your external cladding will only require class O. Okay, so anything beyond 18 meters, then you can go for this BS 8414 test. Okay, so those are the exceptions. Right, so let's get into the requirements. The first one is, remember the external thermocouple. So those external thermocouples will get readings, right, from the fire, right, from the fire source down there. If there are fire spreading on the external surface, then the temperature reading of this thermocouple will be high, right? So the requirements is this. The external temperature should not exceed 600 degrees Celsius for 30 seconds continuously within the 15 minutes fire from start time. And I emphasize on start time because that is a very specific term that is referred to in BS 8414, right? The testing setup and the terminology that they use. So start time refers to a specific time during the test, which Mr. Lau will elaborate further during his part of presentation. So this is the first criteria. So let me just show you an example of pass and fail, right? So the one on the left, where fire do not spread on the external surface, right? So temperature did not exceed 600 degrees Celsius for 30 seconds continuously, right? The one on the right, within only 7 minutes, I recall, fire already started spreading upward, okay? And it actually caused the external thermocouple to read, definitely beyond 600 degrees Celsius. So there is a difference. Let me just extract. So this is how it looks like. So if let's say this one, the fire actually briefly touched 600 degrees Celsius, but briefly did not exceed 30 seconds, right? So this is considered borderline pass, right? So another one is the second criteria is internal fire spread. So same like external, thermocouple, internal thermocouple also should not capture reading or should not have readings that exceed 600 degrees Celsius for 30 seconds continuously within that 15 minutes from start time. Okay, and it is all measured. I mean, the external and internal are all measured in at the level 2 area. Okay, so level 1 is only used to determine start time. Level 2 is used to capture all this reading. And this is how it looks like for the internal thermocouple, right? So based on what we saw, based on our example, it's actually way lower than external fire spread or external temperature, right? Which shows that there's nothing spreading inside, right? So moving on to the third one, which is very qualitative, meaning based on observation. So there should not be visible flame outside of this parameter. Meaning, if let's say you the tester saw fire spreading, outside of this main face from the back, or beyond the main face, top of the main face for 30 seconds continuously, then you fail this criteria, the third criteria, right? So this is also part of the consideration why they need to determine the cavity distance, because if let's say fire is allowed to vent through this place, then you will see visible fire. Okay, so of course, based on the test setup that we saw and done testing on, there was no visible flame observed, right? Be it on the side or beyond the parameter. Okay, so those are the first three. Of course, before I move into the fourth and fifth, those two we need to determine what we call collapse zone, which are areas that are 2.4 meters in width and then 1.2 meters in depth away from the window, right? So this is what we call collapse zone. So anything that falls beyond this collapse zone is considered fail, right? So the first one is mechanical performance. So after the fire has started and they actually set a time 30 minutes. After 30 minutes, then they will put out the fire, and then the next 30 minutes they'll observe whether there's any mechanical failure. So any parts that falls outside of this collapse zone will be considered fail. As straightforward as that. Okay. The reason why is because they don't want any further danger posed to the pedestrian area, because you don't want the cladding to fall and then cause especially those fire brigades cause harm to them, right? So that is one of the considerations. So if it does not fall outside of this zone, then it will be considered pass. This fifth one would be burning debris or pool fire. So similar to that, so it should fall within the collapse zone. The reason is because they do not want fire to spread not just, upward, but also downward. So this is here, following one is an example of how pool fire will potentially spread downward. Okay, so you can see fire, the burning debris actually start spreading, start falling down and then, causing the fire to spread downward. Right, so this is the fifth criteria. So they do not want that to happen. And last but not least, it will be tested if let's say the cladding is installed onto the steel structure. Is that there should not be fire observed at the back of the cladding if let's say it's locked onto a steel structure, right, for 60 seconds continuously. And this is only tested on BS A414 Part 2. Okay, simply because masonry wall tend to be quite solid and withstand quite a lot of heat, right, in that case. So in summary, those are the 6 requirements that you can again find on our website. This is a matter of public interest. So do take your time to actually study it. Right. So with that, I would like to conclude my part and then hand over to Mr. Lau. Mr. Lau, over to you.
Okay, wow, that was a very insightful presentation, Rocky, on the BS 8414. You have also explained how there's a insufficiency of what they call this, to evaluate a material based on just class O alone. So that was very insightful, and I'd like to thank you for that part of the presentation. So now I will take you through the part 2 of the presentation today. I'll be covering 4 topics. First is the sharing of actual BS8414 tests that we did for the Setia City Mall project. Number 2 is the sharing of what caused the fire for Grenfell Tower. Then number 3 is legal consequences when external cladding catches fire. So you got to know that it's not just a fire, there are consequences, legal consequences. Number 4 is the alternative design of external cladding using coated steel. And I will summarize my presentation as the last part of it. So this, let me start with the sharing of Setia City Mall BS8414 test. This is Setia City Mall located at Setia Alam. This Setia City Mall underwent extensive extension work, and also did a very a huge facelift to the existing mall facade using Swissma Senko speed deck in colorbond steel. This is another elevation of the mall. Today, the whole mall is encapsulated or with this speed deck as a facade cladding. The quantity for this is close to or more than 30,000 meters square, if I can remember well. So now the cladding for the mall give it a very fresh look and very revitalized facade. So this is our close-up look of the facade. This one, another close-up look. So for this project, Bomba required that there are 3 tests to be conducted because of the facade, what do you call this, mounting to different aspects of the wall. So the test number 1 is on a part 2 test, meaning to say is actually over a drywall system and not a masonry wall. Test number 2 is part 1, and this is over the existing mall, which is on the masonry wall. The part 1, the part 2, the test number 1 is actually a drywall done for the extension work. So this particular test number 2, you can see that the main structure frame is installed horizontally like a mullion. Whereas test number 3 is again the part 1 over masonry wall. But in this case, the main structure is installed vertically. So what you see here, the blue members are subgirds, which I'll show you in this illustration. So these lip channels are the main frame, and this top head is the subgird. The reason why we need the subgird is because this cladding is installed vertically, and hence we need a horizontal member to receive this cladding for the installation purpose. So this is a SIRIM test report, the front page. Here they document the applicant name. In this case, is the main contractor, the person in charge. Then the product is for external cladding system. Then the reference standard, BS8414 Part 2. Then the method of test, fire performance of external cladding systems, Part 2 as stated. So these are all documented, and description of test specimen. Again, this is a very important part of the documentation. The test specimen consists of Swissma Senko speed deck, metal wall cladding in clean colorbond XRW steel with SP fire stop and drywall system. So in this particular test, there is a fire stop introduced or incorporated in the system. When you do BS8414 test, you have to first submit documentation to SIRIM. Among the documents, one of the most important document is your construction method of your cladding system. So you have to have a very detailed drawings about how you're going to construct this external wall cladding. In this case, for this test, that's a combustion chamber. You can see there's a fire stop which is installed immediately on top of the combustion chamber. There's a flashing below, and then there's a drywall, there's the structure, and then the external facade cladding. So this is another description in the test report. They measure the thickness of the drywall. In this case, is 89 millimeter. The cavity depth is also measured. This is also a very important measurement because the cavity can act as a chimney and propagate fires internally. So the measurement is taken from the back face of the corrugated metal cladding to the front face of the drywall system. Horizontal fire stop incorporated, they also capture the width, the thickness of the fire stop, and also mention where this is located. So when you want to do a BS 8414 test, you are at liberty to incorporate as many fire stop as you like, and you can put it horizontally, vertically to compartmentalize the cavity, what you deem necessary. But bear in mind that whatever you incorporate in the test, you got to implement it in the actual job site. So the more fire stop you need to get the test pass, the more costly is your cladding system. So the external finish is again documented: corrugated metal cladding, the brand Swissma Sanko Speedec, metal wall cladding in clean carbon XRW steel. So the material is also stated. Description of the test specimen. The standard also call for certain dimension that you need to meet. For example, the assembly of the test specimen, in this case, 6 meter above the top of the combustion chamber. So it's minimally 6 or more. So the actual measurement is 7645 millimeters. So it meets the requirement. So the next, again, minimally 2.4 or more is 2.6. So it passed. 1.2 or more, so it's 1.33. That meets the requirement again. And here they also specified or spell out the exact measurement from finished specimen at the wing wall face to the side of the combustion chamber opening, which is now 260 millimeter plus minus 100 millimeter, and ours was 340. The next is the width of combustion chamber and the height of combustion chamber opening. So they want to stipulate that there is a minimum combustion chamber opening that is not blocked. So we meet those requirements. And here is a horizontal joint if present, placed 2.4 meter plus minus 0.1 meter above combustion chamber opening. So they are very specific. If you have a horizontal joint, that it shall be located at this position. And ours, we have a joint located or a lapping located at this 2.4 meter height. And if you have a vertical joint, again, they'll tell you where to locate. That is the minimal requirement. You can have other joints or other lap, but there will be one that is located in the middle of the combustion chamber. So we met all those requirements in the assembly. This is what it's like. You see the test rig, the structure, and at this point in time, the main structure support for drywall is installed. And as you can see, there's a RC beam here. This is a precast RC beam mounted onto this main frame. The reason is you got to actually construct what was on site. And in this project, there's RC beam at every floor. So this is a close-up photo of the steel structure. Just want to show that this is constructed exactly based on what you would do on the construction site. So it's not a makeshift structure. Okay, this is a drywall system. Hence, they infill with insulation. In this project, they have mineral wool. So you can infill whatever insulation you want. But personally, from those incidents like Grenfell Tower, you should avoid having this combustible insulation material or insulation material which has low melting point, because all these will be detrimental or will create problem in your test. This is the inner layer of the drywall, which is a gypsum board. This will be the appearance of the wall when you are inside the mall. This is the external wall. The external drywall is a cement board, a Hume cement board. So this is a close-up look. You can see that they have this element to close the joint. And so when you construct, you also have to do the same. That is the fire stop, the rock wool fire stop, and it's placed directly above the combustion chamber. And there's a flashing below as well. So the next assembly is the flashing or the perimeter flashing around this test rig. So this is a completed version of the specimen that's to be tested, ready to go for the test. This is the test ongoing, captured 10 minutes after ignition, and this is 20 minutes after ignition. So you can see the fire has grown quite ferociously after 10-20 minutes. I'd like to share this video to show you the test after 30 minutes of continuous burning. So okay, so as you can see here, the after 30 minutes, the fire already kind of subsided, right? The peak of it was at this height. Later on, you will understand why at 30 minutes, the fire has already subsided. So this recording the test conditions. The ambient temperature is recorded. The start time temperature was recorded at 27.8 degrees Celsius. And the wind speed is also recorded, because you cannot have wind inside this test rig, because the wind will fan the fire and it will not be accurate. Then the start time, Rocky mentioned the start time. So the test actually starts when the start time reach, when the thermocouple at level 1 register a temperature of 200 degrees Celsius. So when this hit 200 degrees Celsius, the start time the test time will start. All right, the test time actually starts. So in this test, the temperature of 200 degrees Celsius was achieved after 8 minutes and 12 seconds after ignition of the creep. The peak temperature measured at level 2, which is here, was 532.6 degrees Celsius. And it reached that temperature after 10 minutes and 33 seconds. That means if you add these two together, when you start the fire, it's like 18 minutes, 45 seconds that this temperature is reached. But when you start, your timing from start time is 10 minutes, 33 seconds. So peak temperature at level 2, this is at 303 because this is at a cavity, sorry. This is an external cladding. This is the temperature measurement inside the cavity. And that happens 2 minutes later. And they also measure the temperature inside the drywall, which is at 115.8 degrees Celsius, which is a lot lower than the external cladding temperature. So that is the temperature graph. Level 1 is 2.5 meter above the combustion chamber. So you can see that at level 1, the temperature is really, really very hot. Here you can see that it went past 900 degrees Celsius. So if you have a facade cladding or any materials that has a low melting point or melting point within this temperature range, you can expect the product to be melted away. So this is a very important consideration when you construct your wall cladding system. So the level 2 is the criteria for passing, which says that the external cladding cannot achieve a temperature of 600 degrees Celsius. So in our case, is only 532 as recorded. So that external cladding fire temperature pass. This level 2 at the cavity. So this is just to give you how the temperature rises and then drop back over time. And this is inside the drywall, which is actually much, much lower. So test results. This is the summary of the test. External fire spread within the 15 minutes or so pass. Internal fire spread, the cavity area also pass. All these pass means is less than 600 degrees Celsius. Internal fire spread, mid depth of the partition. This is additional measurement for part 2. So also pass. Next criteria, the visible flaming. As explained by Rocky, the flame cannot exceed the confines of the test rig vertically or laterally. And in our test, it was well within the confine. Mechanical performance, again, they will measure whether any objects fall outside the collapse creep zone, or the creep collapse zone rather. So they are very specific. Any object that fall out of this collapse zone with a certain length and weight is deemed fail. And in our test, we pass. Burning, debris, and pool fires. Again, this has to be falling outside the designated creep collapse zone. And in our case, none of these falls out of the zone. So we pass, and also very minimal debris falling onto the zone. This is the burn through. This additional requirement is for part 2 test only, because the requirement on part 2 to assess whether there's any burn through, in this case, the drywall system, and there was no burning through, so it was passed. And overall, this test passed all the 6 criteria. And this is the condition of the test specimen after the test. So the outer surface, you can see that the flame rises and taper off, and this triangular shape. So this is about the distance of a level 1, and that's a level 2, approximately. So when we remove this external cladding, you can see that the cement board drywall system is scotched and closed up. It cracks, but didn't allow the fire to propagate through, so it's safe, and the rock wool is still very much intact. So this is before test and after the test. So I zoom in on this photo here. I just want to highlight this joint. This is a lapping joint. As one of the criteria, if you have a lap, it has to be located at this point, which is 2.5 meter above the combustion chamber. And that's the reason why there was this lap at that particular location. There is also a vertical joint, at this in the center line of the combustion chamber. Next, I would like to share what caused the fire for Grenfell Tower. And Grenfell Tower took place on June 14, 2017. This is a snapshot of how the fire starts and propagates. Like Rocky says, it started, and within 20 minutes, already spread to the top floor. And by the time the fire brigades bring the fire down, is 4 hours, 1:30 to 5:16. So it's about 4 hours later. Very good job done by the fire brigade, considering that the fire is encapsulating the whole building, and they managed to bring it down at 4 hours after the fire. So this is what it looks like, the aftermath of the building. So it's badly burned, and those lower floors that was rescued by the fire brigade. So this is how it looks like on close-up. The cladding is completely burned up, and possibly if it's a low melting point like aluminium. So aluminium has a melting point about 660 degrees Celsius. So it could have gone beyond the temperature and melted the aluminum away. I will share this video for you to have a very quick understanding on how this fire started. And just give me 1 second. Okay.
The blaze started in flat 16 on the 4th floor of the east elevation. It rapidly spread through the window. The first image of the flames taking hold outside flat 16 was taken at 1:09 a.m. It took just a few minutes for the fire to spread up 19 stories to the top of the building. While the fire was spreading upwards, it was also spreading horizontally at a tremendous rate, and in opposite directions, until all 4 elevations of the building were engulfed in flames. The flames met at levels 22 and 23, near the southeast corner of the building. In total, 98 flats were exposed to the flames. 72 people lost their lives in the tragedy.
So that gives you a snapshot of how the fire started and how quickly the fire spread vertically and laterally. So it was quite scary how fast and how rapidly the fire could spread. There is a public inquiry being conducted and still ongoing to investigate on this fire incident. So Sir Martin Moore Biggs is the chairman of this public inquiry, and I'd like to share what he has to say. Just extracted the essential part of his speech.
I find that the principal reason why the fire developed so fiercely was the presence of aluminium composite rain screen panels containing a polyethylene core, which is highly combustible. But the insulation boards and other combustible materials also made a contribution. The architectural crown, a decorative feature introduced as part of the refurbishment, played a significant role in enabling the fire to spread around the building. The heat of the fire on the outside of the building was sufficient to break the glazing and allow the fire to enter individual flats.
Okay, so the heat of the fire is so intense that it can break the glazing. That's how the fire spread from floor to floor. So it's a very ferocious fire.
I find that
So this is a extract of the report by Sir Martin Moore. I quote, "It is clear that the use of combustible materials in the external wall of Grenfell Tower, principally in the form of ACM rain screen cladding, but also in the form of combustible insulation, was the reason why the fire spread so quickly to the whole of the building." So in Grenfell, they not only have combustible ACM rain screen, they also have combustible insulation. They have, in the inquiry, they enlisted the service of Professor Luke Bisbee, and this is his expert report. Basically, the content is about the same as what the chairman says. Here, I just want to read out this part of it that says the ACM product used on Grenfell Tower incorporates a highly combustible PE polymer filler which melts, drips, and flows at elevated temperature. So because all these are so combustible and also it's reached its melting point, that's why it's melting and dripping. And Professor Luke Bisbee conducted his own tests based on 8414 for the ACP. And this is the test I'd like to share starting from 5 minutes 58 seconds. So you can see how fast the fire grows and spread, right? Within seconds, it's just seconds, matter of seconds, not minutes. The fire grow and keep growing until it's so intense. So this is like 30 seconds, which is in normal situation is a very short time. So now at 30 seconds, you can see the flame is exceeding the confine laterally and vertically. So this is coming close to 50 seconds only. You can see how intense the fire is, and you can see that there are facade cladding that is actually been burned through or melted away. So this is just over a minute. And that's it, right? You can see the pool of fires. I'm not sure whether there is any material of significant size and weight that fall out of the collapse zone, but certainly the pool of fires is very significant, as can be seen. And later you can see a sneak peek through after the smoke's gone. Yeah, you can see that the facade cladding here has been burned off. And because this is level 1, remember level 1 temperature can exceed 900 degrees Celsius. So that is a very high temperature. Okay, my next topic is about the legal consequence when external cladding catches fire. So what happened when this fire occurred? Here, I'd like to share the Lacrosse Tower project in Australia. Happens also in the year 2017. The difference between this tower on fire versus the Grenfell Tower is that the Grenfell Tower public inquiry is still ongoing, whereas in Lacrosse, this is the Lacrosse Tower, the fire spread rapidly upwards and eventually laterally as well, very rapidly. The difference is in Lacrosse Tower, Australia, the apartment tower residents already been awarded millions in damage after the cladding fire. So the case already concluded. While nobody died in the blaze, the tower fire sent shock waves through the nation's construction industry and sparked concerns about cladding across the city. So I think it's not only sent shock waves in throughout Australia, it's throughout the world. So this is a precedent case that is already in place. And I think that will be a case that any Commonwealth country can call upon in their argument for any incidents of fire caused by facade cladding. So this is a landmark decision because in this case, the judge finds architect proportionally liable for Lacrosse fire damages. So this case, there is a conclusion and damage, a certain damage, Australian 5.7 million to be paid out to the residents. And these are the people who are responsible for the payment. And this pie chart shows the percentage of the payment to be made by these parties. So just take a look and analyze this pie chart. You have a 3% here, which is rather insignificant, and a 39%. Looking at this group of people, whom do you think is the party that only pay 3%? And whom do you think is most liable to the extent of taking the biggest chunk of the cost at 39%? I give you a few seconds to maybe think about it. See whether your logic works. So a lot of people, just to let you know, the fire was started by a smoker, right? This smoker threw away an unextinguished cigarette butt into a rubbish bin that caught fire and hence caused the facade to be on fire. So he causes the fire, the smoker. So logically, the guy who started the fire should be liable most at 39%. Correct? I mean, that's a rational thinking. But let's go through. The Gardner Group, which is the building surveyor in Australia, they have building surveyor and he's taking 33%. The architects is taking 25%. The fire engineer is the one that's most liable. And I think the reason is very clear. They are called a fire engineer, and their main task is to ensure that the building is fire safe. So the smoker got away with 3%. So in Malaysia, we do not have building surveyor, but we have quantity surveyor. So the quantity surveyor at times also do specify the facade cladding. So what is the implication of them specifying facade cladding if something go wrong? What will be the cost sharing percentage? I don't know. Architects in Malaysia, for sure there is an architect, and usually they are the one who specify or select the facade cladding materials. Fire engineer, we don't have. I think at best for facade cladding, we have facade consultant. So whether the facade consultant is going to take over the fire engineer or the architects is assuming the biggest part of the responsibility, I'm not sure. So you got to really figure this out. Whatever it is, the story is all these consultants are responsible if there is a fire to the facade cladding. So alternative external cladding system using coated steel. So my last part of sharing is to give you ideas about what kind of facade cladding that you can also explore. In countries like Australia especially, and also in America, they often use trapezoidal metal deck cladding, like this project, Emerald Hills Aquatic Center. Back home, the Mercedes-Benz showroom in Selangor is done using our Swissma Senko sinusoidal in colorbond steel. You can't see that very much, but the whole building is cladded with that profile. And this Setia City Convention Center too is done using SpeedDeck in colorbond steel. We have a metal tiles system called duct metal tiles. It's a concealed interlocking fixing system with 3 designs to choose from: diamond shape, rectangular, and rhomboid. So if you have a masonry wall, you could construct the system using these metal tiles by incorporating a metal deck as the support layer or the layer to mount on these metal tiles. This Gezi Hotel in Turkey incorporated this metal tiles system as a facade cladding. So that is from far, and close up you can see is very nice looking. Our office in Shah Alam is also using these metal tiles in colorbond steel. It actually enhanced the aesthetic of our office facade tremendously. This is a metal tiles cladding bricklay pattern. So these are the rectangular shape done with the bricklay pattern. Prime Minister's residence in Putrajaya is using a dark metal tiles roof. And you can see that this rhomboid shape is very interesting because you can see that the roof is like undulating or is dancing. Actually, it's just an optical illusion because it's flat. So can you imagine you can use this on the roof? You can also do it on the wall cladding. We also have this standing seam called Swissma double weld standing seam that can be used for roofing and wall cladding. So this profile is very versatile. It can be tapered and curved, and there's a concealed sliding clips that can allow for thermal expansion, and it's completely leak proof. As you can see here, it's double folded. So example of a standing seam cladding can be like this, right? The lines are joints of this, a circular building, because the standing seam panels can be pre-curved or can be tapered, so it can fit any geometry. In this case, it can be a perfect a system for cladding a circular building. Back home in Penang, we have this swimming club where the cladding is done in standing seam. You can see it's curved. It's even curved and tapered and torpedoed shape. So it's a very versatile cladding that you can use for any geometry. You can do it as straight panels, in this case, clubhouse. Or you can do it like what they do in this university. You can vary the panel width to make it more interesting. Or this Dickinson College, right? You can have a wider panel and narrow panel to create a design. Back home, the Alameda Shopping Center uses the standing seam, Swissma double weld standing seam for the roof, as well as for the cladding. So the Link in Kuala Lumpur, a very vibrant color building. This project is using our Swissma snap weld roofing and cladding system. So this can be used for roof and for wall cladding. We also have this Swissma cassettes interlocking panel, which is actually using a tongue and groove joint as silicone free, and it's very fast and easy to install. An example of the system could be on the masonry wall with a subframe and just direct fixing, very straightforward. It can appear to be like this. This kind of design can be in the form of interlocking panel like the cassettes, or it can be a standing seam, or it can be a snap weld. So back home in D7 Kuala Lumpur, we have these Swissma cassettes in colorbond steel, laid horizontally. So you can see that it offers a very differentiated kind of aesthetics to this building, close up. And KDU College uses the cassettes cladding, but in a vertical format. And you can do for industrial building. This is a factory using the cassette system, and this is a condition imposed that there should be no lap, although it can be lap, and this is 16-meter length. So I'll come to the end of my presentations. First, I would like to summarize the first topic. So we have done the test under BS 8414 for the Setia City Mall project. And in that test, the 0.42 BST Samco speed deck in colorbond steel passed both the BS 8414 part 1 without fire stop. Yeah, we did the part 1 test, the 2 part 1 tests without fire stop, and we passed. Whereas the part 2 test was tested first, and fire stop was incorporated because as a security that we will pass. But nevertheless, after seeing the results, there was confidence that we can do away with the fire stop. So for the second topics, the key message is, moving forward, regardless of whether the cladding material pass BS 476 part 4, which is incombustible, or pass part 6 and 7, collectively called class O, the cladding has been tested under BS 8414 because it is now a system test instead of material test. So the class O classification can be insufficient to gauge whether the material is actually going to be safe to be used as a facade cladding. In the test for BS 8414, I just want to highlight that if you do a system, like I said, you have to inform or spell out what kind of cavity depth, what insulation, if you do add on insulation, right? And then your choice of external cladding. So if you vary the insulation thickness or the density of the insulation, the bomba or might call for a retest, because everything being the same, but if you change these two parameters, you might be asked to do another test. If your cavity changes, you need to do another test. and the position of fire breaks. All right, if you have incorporated 5 horizontal fire breaks and you take away 2 and everything else remains the same, I think they will ask you to do another fire test. But logically, if you have 1, you add another 1, I'm not sure whether Bomba will ask you to do another test, because you are actually enhancing the performance rather than the other way around. So all these, I think, will be subject to discussion with Bomba. If you have already a test and if some element change, technically you're supposed to do a retest. So the third topics is sharing, because this is already a precedence case. So be mindful of the legal implication. Avoid unsuitable cladding system that cannot meet BS 8414. So like I said, precedent case already set in Victoria, Australia, where the tribunal says the architect, engineers, and relevant parties are made to compensate for the loss arising from the fire incidents. So this, in other words, somebody has to be responsible, and they find that the people entrusted to construct, to design the building and to ensure the building is safe are the people responsible for the safety of the facade cladding. Lastly, I've shared the other options of facade cladding using coated steel, incorporating innovative and versatile systems such as Swissma Synchro Speedec, Swissma double weld standing seam, or the cassettes interlocking panel with or without fire stop. So maybe it's time to explore alternative facade cladding system and material. So with that, I end my presentation. Thank you. Rocky, I'd like to invite Rocky back. So thank you, Rocky, for accepting our invitation to be our guest speaker today.
No problem. Glad to be involved in this talk.
Yeah, so am I. So I think BlueScope Steel and Swissma, we have done a lot of joint presentations on technical subjects. So if you like this presentation, do give us a like in our Facebook. If you want more information on our product, you can log on to our website, www.swissma.com. Or for now, you can log into this Archidex online. You can go to our booth and explore what is there. We have products information there as well. And if you have any questions regarding this presentation, feel free to WhatsApp me or to send me an email. I'll be happy to answer you on that. So with that, Rocky, it's time to say bye-bye to our audience. Bye.
Right. Bye-bye.
Bye, everyone. Take care. Stay safe.